This presentation was developed because we do a lot of talking to folks about FDR, obviously with cement, in the Southeast. And as a result, what I find is a lot of folks are into the equations, but they haven't developed that intuitive feeling for pavement and thickness and things like that. So this presentation is primarily to try to help get your mind wrapped around it. But that said, there are a lot of different ways to skin the cat as far as coming up with pavement thickness. So this is more, as I put in the description, a conceptual framework, which sounds much better than just a way to think about it. But the idea is more the way to have a thought experiment about it. But your numbers themselves may vary a little bit. So with that, we're going to talk about thickness and how thickness affects the performance of pavement. As I said, this is sort of a cement-centric presentation. However, curves are very similar for asphalt-based materials. So again, the whole thing will work sort of the same, but sort of different. So first, to step back and look at the really 60,000-foot level. What does a pavement do? And really, the first set of things, and the things that most people, when I sort of ask this question, think about, is the functional aspects. It's got to be smooth. It's got to have good friction. It shouldn't be noisy. It shouldn't be rutted. And those are very important things. But in a lot of cases, rutting being kind of a hybrid, you can have a rough pavement that's structurally very sound. It may have terrible functional aspects, but it may have great structural aspects, or vice versa. You can take a road that's really in poor shape and do microsurfacing on it, and when a week later, when the pavement management folks come out and rate it, it's going to look good, but is it really going to hold up? So what I want to talk about is more of the structural aspect of things. So in the early days of pavement design, when the whole field was being invented roughly 100 years ago, the original goal was to get the farmers out of the mud. And so the concern there was initially to protect the subgrade from permanent deformation. You don't want whatever's underneath the pavement moving around on you. You want to get it to where it stays stable. And in the early days, that was really where pavement design mostly went. But as loads and traffic numbers started to increase, certainly by the 50s, for more busy roads, fatigue resistance comes into the equation. What you have to imagine is like taking a coat hanger and flexing it enough times, eventually it'll break. It's the same thing with pavement, certainly bound pavement layers. You flex them enough times, they'll start to fail, even if they are, in theory, protecting the subgrade. So how does a pavement do this? And there's sort of two ways about going about it. And I'm not saying that one way is better than the other. They both have their pluses and minuses. But sort of on one end of the equation, you're looking at flexible pavements. And really, asphalt is sort of flexible in the sense that the coarse aggregate skeleton is what supports the load. You put a load on top, and what's underneath it is more rocks, and those rocks hold it up. And then the next set of rocks holds that up, and you keep doing that until eventually you spread the load out enough that whatever's underneath isn't getting damaged by that. And if you have a softer material, you just stack more rocks on there. You get a bigger load, you stack more rocks on there. And really the aggregate, or the fine aggregate, and the liquid is as much there to hold that skeleton in place as it is to provide strength. Now that's not entirely true, but just like if you take a physics class and they talk about frictionless surfaces and massless springs and things like that, there's no such thing as pure, but in this case, that's kind of how it works. So typically, if you have your load on top, what you end up with is 100 psi contact pressure tends to be reduced to about 20 psi, 20, 25 psi, and roughly a 30-inch surface area or area underneath. So if you have a relatively stiff subgrade, or you can put granular material underneath, that's great. Now, when we talk to folks about chemically treated or chemically treated base materials, then what we're into is something where instead of having that aggregate skeleton holding things up, what you have is a resistance to bending. So in a rigid or semi-rigid base type thing, what you get is that resistance to bending out here is what's holding up the load, and you have a lower pressure underneath. But obviously all the forces have to add up. So in the end, what you end up with is a much larger area of influence for your load. And this is both a bug and a feature in these sort of pavements. It's a feature because obviously you're putting less pressure on what's underneath. It's a bug because if you have a problem in that pavement, 10 feet away, things may start going wrong. So if you can imagine that as this wheel rolls along here and it gets to the end, all that load is kind of going to pool up right there at the end. So load transfer efficiency at discontinuities in this sort of base become very important. However, for most pavements in general, what you have, and I'm sorry, I really need to make those arrows bigger in this picture, but when you have a load on top of your pavement, it's typically in compression right under the load, and it's in tension at the bottom of the layer. And then out at a distance on top, it's in tension, and at a distance, it's in compression at a much lower magnitude. So again, if you imagine this wheel rolling down the road, and this is whether it's a flexible asphalt or a stiff cement-treated layer, what happens is that layer is constantly undergoing a kneading effect because suddenly it goes into compression, and then it's into tension, then it's back into compression again. So it's kind of a back and forth motion, and that's where you have to worry about how things work. So these days, for higher type roads, for most pavements with bound materials, fatigue damage is the controlling factor. Now, I'm sure you can find exceptions to this, but for most roads, it's my experience is the fatigue damage is the controlling factor. And this may seem sort of obvious, but the larger the stress or strain at your critical point, the fewer load repetitions you get to failure. And so that's ideally, you either want to have fewer stresses and strains on the pavement, or you want to reduce them through your pavement design. So the relationship between material response and damage is what they call a transfer function. And every time I talk about this, I'm always reminded of the old Steve Martin comedy routine. I'm old enough to remember when it first came out in the 70s. And he used to do a thing about, how to get $1 million and not pay taxes. And step one, get $1 million. Step two, don't pay taxes. And it's the same thing with a transfer function. You can say, you just work out the relationship between failure and forever, and pencil that in there and call me when you're done. So it's not that simple. These are complicated things, but still, from an intuitive sort of thought experiment perspective, you can still kind of work on this. So, you have two endpoints in any pavement design. And at one extreme, you can have a pavement that'll fail the first time you use it. You see this more in airfield type pavement where you've got really heavy landing gear loads that can punch through a pavement from the get-go. I personally have never designed a pavement that failed in one load repetition. My own personal record is 8 hours. That was not a good day, or 8 hours, especially because it happened on Interstate 85 over Memorial Day weekend, and so it was a temporary pavement. It was supposed to last 3 days, not 8 hours, but anyway. So this typically is not a problem for most highway type pavements, but at the other end of the spectrum, and Dr. Powell from NCAT talked about this a little the other day. At the other end of the extreme, you can have the load-induced response in that pavement be so low that you more or less consider it to have an infinite fatigue life. Now, does that mean the pavement lasts forever? No, there's still environmental factors, there's still natural variation in the field from the construction, the traffic may not be what you think, whatever. But from a pure perspective, if you stress your pavement so little, it should not fail from a fatigue relationship. And this ideally, if you can get to this point at a reasonable cost, that would be nice to have. I had a civil engineering professor many years ago who once said that a civil engineer is a person who can do for a nickel what any damn idiot could do for $1. And so, you can always design a pavement to be 28 inches thick and have 5 layers, and it might work, but you really need that for a residential neighborhood. So the key is to try to get there cheaply. So in asphalt, and again, Buzz spoke about this yesterday, the infinite condition is determined by what's called the endurance limit, and it's expressed in microstrains. He said sort of how much you're stretching the asphalt. And so typically, there's some variance. You can always find researchers with different numbers, but typically 70 to 200 microstrain is considered a perpetual condition. And again, it depends on the mix design and some of your other conditions. For cement-treated bases, or really chemically stabilized bases, the fatigue life is expressed as the ratio of the horizontal tensile stress, I really should have put the word tensile in there, to the modulus of rupture. Modulus of rupture is pretty much where you're looking at the tensile characteristics of a cement-treated material. Concrete, again, use the thought experiment here. Obviously, concrete likes compression much more than it likes tension. So tension, even in a cement-treated base, is an issue. So you want to keep that tension in that material at a relatively low proportion of what it takes to bust it. A lot of models assume that if you keep it below 45% of the modulus of rupture, that you shouldn't have failure in fatigue. And again, different models pick a different number, but it's somewhere in there. So here's a typical pavement. South Carolina predominantly uses cement-treated FDR. We have a long history in South Carolina of cement-treated bases. South Carolina did the first scientifically designed cement-treated base in 1935. It's still in service. They did 3 or 4 projects, and most of them that we can still find are out there. And so that's what we do a lot of, so this is sort of what this example is, but you can do it with other materials. So here we're assuming our unconfined compressive strength is 400 psi, and that works out to be a modulus of rupture of 139 psi, and that's another one of those get $1 million type of things. There are a number of different correlations between modulus of rupture and compressive strength, so you may have a different one, and that is not something. I'm not up here to necessarily push one of those models. This is just an example. So what is it David Letterman used to say? This is a demonstration, not a competition. Please, no wagering. So please don't build a pavement based on this necessarily. And the modulus of elasticity would be about 600,000. So if you go through the math magic on this thing, what you end up with is a horizontal stress of 51 psi in tension at the bottom of that layer. So at that critical point, you're looking at 51 psi, and that works out to be horizontal stress to modulus of rupture ratio of 0.38. So we're under that 0.45 level. Of course, this is a synthetic pavement. I can control all the numbers that go into it, so you can imagine. I picked one that would come out this way. Obviously, if your subgrade is weaker, if your chemically treated layer is weaker, if your asphalt layer is thicker or thinner, all these numbers change. But again, please no wagering. So we got a 0.38 out of this particular design, and again, there are a whole bunch of different transfer functions out there. This is the original AASHTO MEPDG transfer function, which is uncalibrated. My understanding is they introduced a new calibration for this last week in Denver. Unfortunately, I wasn't there to see it. So I don't know what the new magic numbers are. So it's not the absolute numbers here that matter as much as the change caused by additional increments of thickness. But in theory, you should get 14.5 million 9 kip wheel loads on this pavement to failure. And if you look at the microstrain in the asphalt, in this particular instance, it comes out to be 83, which is, again, below the typical endurance limits for fatigue. So And as we mentioned at the beginning, the vertical stress on the subgrade is 5.5 psi. So it's protecting the subgrade reasonably well in theory. And here's how it works. This is tension, this is compression over here. Your neutral axis is right about here. And then you've got a discontinuity here between the asphalt and the FDR, which is where your shear stress would come while you have to tack the asphalt to the top of it. So now here's the effect of changing the thickness of that layer. As you can see, if you went in and did 3 inches, and cement-treated bases are by their nature brittle. They may have a high stiffness, but then glass has a high stiffness too, but obviously you make it thin enough, it's very easy to break it. And it's the same thing with a cement-treated or chemically stabilized base. In this case, our tensile stress would be 181 psi. That's a 1.3, so this is your famous break it on the first try type pavement. 3 inches probably wouldn't work. But you bump it from 3 to 6 inches, your tensile stress drops to 100, which is below our 139 number. And so you get a 0.71 ratio, and that works out to be about 1,200. So it's not going to break the first day, and I don't know, maybe if you only get 10 loads per day, that's still only about 120 days. So I don't know, it depends on how fast the check clears as to whether this one will be good. But anyway, but then you do increase it by a factor of 1,200 when you change it. Now you add another 2 inches, go to 8 inches, and you're looking at 400,000. So you've pretty much increased it by a factor of about 30 to 35 in this case by going to 8 inches. Add 1 more inch, go to 9 inches, the stress drops to 61 psi, you're at a 0.44, which again in some models would go to infinite. However, in the particular one I picked for this, and I picked one of the more pessimistic ones, you're looking at 3 million. So again, now you've gone from 400,000 to 3 million. So you've got an increase of roughly 6 or 7, going from 8 to 9. So again, just 1 inch will typically get you a lot more life. And again, the previous Dr. Andrew pointed out that above 10, the life increases greatly, and we can see that here. You jump from 9 to 10, and now you've gone from 3 million to 15 million. So again, a factor of 5 increase on this one. And then 12 inches, you're at 197 million, and a 0.29 stress ratio. So you shouldn't break that layer by running traffic loads on it. Now, there are a lot of other ways to break a layer, of course, and this is really a super simplified mechanistic design because there are superimposed stresses caused by temperature, caused by the curing process of the base, all this sort of thing. So as I say, it's demonstration, not a competition. Please, no wagering. But this again hopefully gives you a feel about why it's important to go thicker. I used to joke when I was the pavement design engineer in South Carolina that if more was better, then too much was just right when it came to pavement design, because you've never seen a newspaper headline that says pavement lasts much longer than expected, no delays today. But the opposite, certainly when you design an 8-hour-long pavement design, you're on the front page of the paper, and not in a good way. You're never on the front page of a paper if you're a pavement engineer in a good way. It just doesn't work that way. So if you're going to err on the side of anything, err on the side of too much, not enough in this particular case. That said, of course, you want to look at your relative costs going up, but typically, at least in South Carolina, where we do a lot of this, up to a point, adding extra depth doesn't really add a lot of extra cost. We let our material separate from the stabilizer, so you end up using maybe the same stabilizer, but less strength overall. But typically the tensile stress goes down faster than the strength ratio goes up, if that makes sense. And we, Stan Bland and I travel a lot together and give a lot of talks, and we went to a place that I will not name. It's not in South Carolina, but it is in the Southeast, where they were having a lot of trouble. They said, well, we're going to quit using, in this case, soil cement bases, because they're in a place where aggregate has to be railed in from 100 miles away. They don't have any source of it, and they do a lot of soil cement. And we said, well, you know, what happens when you get a poor performing soil cement? And they're doing it 6 inches thick to start with. So, you know, and the soil cement is not as strong necessarily as what we're talking about here. So their stress ratio is not good, and they're having failures. However, I will say I have designed 6-inch FDR jobs that lasted a lot longer than 1,200. So I think these numbers are pessimistic. But, you know, and they said, well, if it doesn't work, we go in and do it, but we put more cement in the next time, which, you know, working for the cement industry, I would think, hey, that would be good. But the problem is they just keep throwing more cement in there when they really do better to go deeper. And so that's kind of what we're preaching here. And again, you know, even when you're talking a granular type base, it's a similar thing. So there are a lot of pavement design procedures out there. It was mentioned the MEPDG. It looks at the effects of pavement materials, but it has to be calibrated, and that's been the problem. There are also a number, again, for those of you that are doing the AASHTO design equation, there are a number of different coefficients out there. South Carolina, where I come from, uses a 0.26. Virginia has done a lot of research. You're going to hear from Brian Diefendorfer later. And they use a 0.3. NCAT has looked at it and comes up with a 0.37. Which one's right? Well, the answer is all of them. South Carolina, especially back in the good old days before I was enlightened, used to build a lot of 6-inch reclamation. And so, yeah, our coefficient needs to be lower, whereas maybe NCAT was looking at a foot thick, if I recall right, layer. That's probably right for a foot thick. It doesn't really, if you use a single coefficient approach, you're only looking at something that does one sort of equal increase for each go-around. So this is a really brief pavement design course. Again, I could go on for a lot longer, but I think I'll wind it up here for time. So are there any questions or anything you want to throw at me? Yes, sir.
How much does in-place density affect those values?
A lot. We also, and I don't have any specific research on cement-treated bases that have variable compaction, but there was some work done on other cement-treated bases, mostly for dam construction. And what they found was that, say you only compact the material to about 80% of the density it's supposed to have, you only get about 20% of the strength. So appropriate compaction with a cement-treated base or chemically stabilized base is a key acceptance factor. You've got to compact it if you want it to give you the strength that you're assuming you've got in the first place. So it is critical. Yes?
Beyond 12 inches, we find in FDR that a lot of times subgrade instability will dictate the thickness of the treatment versus structural layers.
Exactly.
Is it fair at that point to recalculate the strain coefficient?
Well, the issue that you run into, I would think, would be how can you successfully compact much beyond 12 inches? So 12 inches has been kind of a practical maximum. However, there are contractors, and I had some experience with it again while I was still at South Carolina, where we would go deeper. The equipment can mix deeper, but we only really worry about the compaction on the top 12 inches. So we've seen where we've gone 20 inches of stabilization, but we are not assuming we get full compaction on those bottom, say, 8 inches. I mean, practically speaking, it's hard to find a nuclear gauge with a long enough probe to go to the bottom of the layer. And so, at least in where I am from. That has been successful, but you really have to consider it more of a modification as opposed to a stabilization under that layer. And then there are other things you can do, but you're right. In a lot of cases, you have to have something to compact upon to begin with. But if you're doing FDR, you're hopefully on a road that they've managed to build on it in the first place. So, but that's often wishful thinking. Yes, sir. You mean as far as how much goes over the FDR? Yes, exactly. The more asphalt does get you more credit. And you know, there's some cases on low-volume roads where, again, in South Carolina, we've successfully done chip seals. Keep in mind, we don't do a lot of plowing for snow in South Carolina. We close the schools when the wind chill drops below 20, or at least have delayed opening. So no one owns jackets heavy enough for that. We just all stay home till it warms up. So, you know, you know, your mileage may vary depending on where you are, but yes, you do see that reduction in stress underneath, and that's an alternative way, you know, and in many cases, again, what's been done in Virginia, they'll mill up what's there and do a cold central plant recycle while they do FDR on what's there, and then, you know, they end up with 8-10 inches of asphalt over the top, and so it's all how you design the system. Yes, sir.
We were talking about the micro strains, the 70 to 200.
Yes.
You said mixed type is a factor of that?
Well, yes. I mean, that was part of what Buzz Powell talked about the other day, was that the cold recycled material was behaving in some cases more like a granular material than like an asphalt. So it does depend on the behavior of your mix. But now keep in mind, I'm not an asphalt guy, so I just copy the bullet points from other people in that case. But my understanding is the mix design does make a difference.